Hello class, today I'm going to show you how we can simulate material with some plasticity. Okay, let's start with workbench. So we are going to have a nonlinear plastic deformation, and because we want to have like a simple case, I'm going to draw a beam, and it is going to be a cantilever beam. So let's see. One side is going to be fixed to have fixed support, and I'm going to have uniformly varying load over that beam. Later when we are drawing, I haven't decided what geometry or cross-section shape we want to have for now. So later when we are drawing, we are going to make a decision about that. And by applying this load, we are going to have some stress and strain over this beam. Usually up to this stage, we worked about this elastic region. So we increased our stress up to yield stress, and everything was linear, and if you release the stress or pressure, it is going to go back to the zero. If you continue the stress, we are going to have plastic region, and we are going to out of this elastic region like this, and it is by continuing the stress or pressure, we are finally going to reach a fracture point. For this example, I'm going to do this. Increase pressure to pass this yield stress, enter to the plastic region, and release the load. By unloading, because we already are in plastic region, we are going to have some deformation, so that is why we are going to have some plastic deformation here, and by unloading, the starting point is going to start here. Again, if we start loading again, we can start from this point. So for this analysis, I'm going to increase stress up to this point and unload. So it is going to have two steps. One more point I would like to mention, we always use true stress strain curve, because usually we have two types of stress strain graph. The one we call engineering stress strain curve, which is the definition is applied force over original cross section, and we have true stress strain curve, which is based on applied force over changing cross section area. Usually or always we use this true one. And we can have several different model. As you can see here, we have some curve graph here after this yield point. You can convert this yield, this A to B point, to a one line, or you can convert this curve to two lines. So two lines is going to be much more accurate. So here, when I say my material is bilinear isotropic, it means after elastic region, which I reach to this yield stress, the bended curve area is going to be one line. So we approximated that curve as one line. If I say I want to use multilinear isotropic material, instead of having one line, we are going to have two lines here. So two lines with two different slopes, which is going to be much more accurate, but the number of calculation is going to be more and more time consuming. Yeah, so we have enough information. Let's go back to our static structural. I would like to assign my material. As you can see, this is structure steel. It is isotropic elasticity. And let's go for open plasticity area. Let me close these. So inside plasticity, you can see bilinear isotropic hardening, multilinear isotropic hardening. As we discussed, this is one line after elastic regime. This one is going to be two lines. You can easily drag it to properties, and it's going to appear here. And for example, let me change the unit. Where's megapascal? Here, both of them. So for example, 250 megapascal for yield stress, 1450 for the slope or tangent module, and it's going to draw our stress strain diagram here. This is the elastic part, which is up to 250 megapascal, and the slope for the second part for this bilinear isotropic material, which I decided to be 1450 megapascal. Or instead of defining everything, we can select from the ANSYS library. So I'm going to delete this one. Go to ANSYS engineering data resources, general nonlinear materials, and if I look for stainless steel or structural steel, let's see structural steel. So this NL is going to represent non-linear, and let's add this to our properties. So if I turn off that one, so I'm going to have structural steel but non-linear. And if I click over bilinear isotropic hardening, you can see the data for this bilinear. Or you could select multilinear, which is going to be more accurate. Okay, we are happy with it. Let's go for and find a geometry. Okay. Let's start from the center. Let's go 50. It is going to be 5 centimeter. Yeah. Let's go 50. And then $30 up, 25 here, 10 here, 15, 10 here, 40. This is just random profile I selected. I could extend this one to 30. Yeah. Even let's make this one a bit thinner because I want to have deformation. Okay, this is going to be weaker area. Later, it's easier to show it. 500, so half a meter, 500 millimeter, so half a meter beam. Let's finish this with the drawing. Open model. Okay, now it's ready. Because of your first project, definitely, you know, the first thing you should do is taking care of this question mark for geometry. ANSYS didn't assign the material, so structure still nonlinear is assigned. Mesh. Let's see the default mesh. It's very uniform, which is good, but very large. If I keep this mesh size and apply large pressure over this beam, ANSYS is going to give me some errors and telling me these meshes are very elongated and bended, and that is why I'm receiving some errors. It's a good idea to choose once this default mesh, apply the pressure, and then refine it. And you know what's the reason. Remember we talked during the lecture, the reason if we had a non-uniform mesh and those mesh were like stretched, they are going to create an inaccuracy for us. And for this case, because we have plastic deformation and this mesh size are very large, by plastic deformation those mesh are going to be stretched a lot, and ANSYS is going to start giving us some errors and asking us to decrease the mesh size. So let me select the geometry. What was the default? 25 millimeter. Let's go with 8. Even I could go lower, like a 4. So twice smaller. Yeah, good enough. We are going to capture more details here. Okay. We take care of mesh. Now let's take care of the analysis setting. As you remember, I want to have 2 steps, because one loading up to B and then unloading. So I'm going to have 2 steps. And let's turn on the auto time sampling. The number of sub-step, let's go with 30, minimum 30, and maximum 100. And also I need to turn on this large deflection, because we have plastic deformation. Our deflection is going to be large. If we let ANSYS to make those decisions, we are going to have some inaccuracy. So it's better to let ANSYS know we are going to have large deflection. Okay, this is for current time step, which is number 1. For number 2, we don't care, because it is just unloading. We don't need any refined number of sub-steps, take care of the like a behavior. First, when we are applying the load, the details are important for us. For unloading, we don't care, just unload it. So good enough for us. Now let's add some support, fixed support for this one. Apply, and I would like to apply pressure over the surface. So pressure. As you remember, I want to have uniformly varying pressure here. So instead of putting magnitude, I'm going to select tabular, and for first time step, let's have for example 1 1 megapascal. For the second one, 0. So the second one is going to be unloading. And independent variable is going to be z, because I want to have a variable load over this beam. So these are numbers, the initial numbers. I don't know what are these numbers. Just ANSYS add these numbers as default. But I know the length of my beam is 500 millimeter, and it is going to be one or half. Yeah, 1 megapascal here, and 0 at the other side. Okay. So let me go back to the time. So this is going to be 1 for the load, and for the second time step it is going to be 0. So releasing that load. Yes, let me check once more. Time is 0 and 1. For z is 1, 0 and 1. Okay, good. So this is our pressure and our support. For the results, I'm going to where's the stress? One equivalent stress and strain, total strain. Now let's solve it. It is going to take some time to solve, and it depends on the steps, the number of steps you selected. So I'm going to pause it and come back after finishing. Okay, we are back and our simulation finished. As you can see, we have plastic deformation about this point. Let's see, and this is true scale, so we really have deformation there. If I make it twice the scale, it is going to be much more clear for us that we have some deformation. Remember, when I was drawing the geometry, I intentionally decreased the layer here to have like a weakness there, to be able to see some deformation there. And we can see the video. Let's see, when we apply force, let me increase frames to 100, and now it is going to be better. Okay, if you want, you can save this video using this button. We also can see the strain here. The maximum is 0.04. Now let's draw stress strain diagram. Remember this stress strain diagram here? I want to draw this for our case. Let me find the maximum point. Where is it? So maximum point is there. If I had finer mesh, this maximum point may change a little bit to left or right. Yeah, but it's okay. So what I want to do, I want to draw stress strain diagram for that point. So let's insert stress, equivalent stress, and select this node selector. And this is the maximum stress point, so I'm going to apply the geometry for that node. Then I can right click here, insert where's the strain and total strain. It didn't select, so I need to manually ask him to do it. Now let's solve it. So basically I selected stress and strain for a specific point which we know we had maximum deformation. Let's select these two and click chart. Now it is going to draw a chart for us here. Let me take care of x-axis for stress and strain diagram is strain, y-axis is stress. So instead of time, it should be strain, maximum strain. I don't want to see time, so double click omit. I don't want minimum. I don't want also minimum strain. Okay, as you can see here, now we have stress strain diagram for the material we had at this point. This section is the linear initial section up to 250 is going to be elastic, and then we have one line. Remember, we selected bilinear, so that is why we have one line there. It's a plastic deformation, and then at this point we are unloading. It's coming back here. If we were in the elastic region, by unloading, everything is going to go back to the origin. But for plastic, it's going to come back, and we have some plastic region here. Okay. Let's go back to stress. Okay, enough for this one, and see you next time.